We now discuss the basic combinational logic circuits, and we say that we use basic gates in combinational logic design, but in a limited way to provide or to create simple circuits that may consist of 4 or 5 inputs and a maximum of around 3 outputs. And for more complex circuits, the use of basic gates like AND, OR, and NAND and NOR may prove to be very undesirable because they can become quite complex. And that is why we prefer the use of ICs that consume less circuit board area. The associated wiring and interconnection of logic gates, if they were used to create a complex circuit, can also become quite extensive. And these limitations therefore led to the development of IC logic modules at the MSI level. MSI means medium scale integration. And the development of these ICs has allowed building of more complex and compact combinational logic circuits. The most popular or widely used logic modules under the combinational logic circuits may be recognized as multiplexers, demultiplexers, encoders, decoders, arithmetic adders, and magnitude comparators. And you're going to be looking at these combinational logic circuits, their design, their use, and their operation. So the first one is the multiplexer. And we say that the multiplexer is a combinational logic switch that connects one output line to several input lines. And we always say that the number of input lines is normally given as a power of 2. And we will see first and foremost an example of a mechanical switch that can be used to illustrate the function of multiplexer. And the commercially available multiplexers. The commercially available multiplexers range from those with 2 input lines to maximum of 16 input lines. And we will start with a 4-line to 1-line multiplexer and use our mechanical multiplexer analogy to illustrate its functionality. And we see that a simple mechanical analogy of a multiplexer may be illustrated by a mechanical switch that has 4 input lines, I1, I2, I3 to I4, and a rotary switch that selects any one of the input lines and provides a connection to the output line. It is for this reason that a multiplexer is also referred to as data selector switch. So look at this mechanical switch. It has 4 input lines starting with I0 all the way up to I3, and this is the rotary switch that rotates amongst the four input lines. When you want it to connect to I1, you just rotate your rotary switch, and the output line is connected to the line I1 or I2 depending on the selection that has been made. So one of the typical use of multiplexers that is much or easily to illustrate is the radio tuner. So what the radio tuner does is that the radio is able to receive multiple signals, maybe multiple FM signals, but depending on the point where the radio tuner is selected, we are able to only listen to one station, and therefore our output line is a speaker, so to speak, which is connecting to one FM station. So we have in the FM 101, FM 102, all the possible FM stations that the radio may receive. But the tuner is the one that acts as a multiplexer, selecting one of the many inputs that are available at the radio receiver. So that is the basic, simple mechanical analogy of a multiplexer. And the digital multiplexer works in a similar manner, such that it has multiple input lines that may be connected to one output line, and the output line is or receives the signal that is coming from that one single input line. Now, our 4-line to 1-line multiplexer may be illustrated as shown by this diagram. And we say that it is a 4-line to 1-line type because it has 4 input lines and 1 single output line. So as you can see, there are 4 of the input lines and 1 output line, but there is an additional select input switches that are used for determining which of the input lines that are available we are connecting to the output line. We notice that the mechanical switch that we have illustrated earlier may be too slow and make poor contact, and therefore quite unhelpful when working with digital circuits that are quite fast. And therefore we use a 4-line to 1-line multiplexer that is implemented using basic logic gates. So in order to select any of the 2 power n input lines, we normally use an n-bit code, and it's dependent, n is dependent on the number of input lines, or we say that the number of input lines are defined by the number of select lines that are available at the multiplexer. So for instance, let's say we have 4 input line, like we are mentioning here, and therefore 4 input line is made up of 2 n is equals to 2, and therefore we will need a 2-bit code to select any one of the 4 input lines. And these 2 input lines are designated as S1 and S0 when they are used to identify any of the 4 input lines I0, I1, I2, and I3. And the select lines may be represented by a truth table of 4-line to 1-line multiplexer. And the truth table says when you select or you set the input lines to be having 00 as the select line code, then we know that what is going to be connected to the output Y is I0. When we select 01 at the select lines, then we know that our output Y is connected to the input line I1. And similarly, when S1, S0 is set as 11, then we can say that the output line is connected to the I3 input. Therefore, we may express the output equation of Y as a function of the select lines S1 and S2 together with the input lines I1, I2 all the way to I3. And we say that when the select lines S1, S0 is given code 00, the output line becomes I0. I think that is what I have already said. And therefore, we are saying that we can come up with a function that represents the multiplexer as output as being a function of the select lines and the input lines. So we can simply say that Y is going to be given by when S1 is bar and S0 is bar, then we are saying that the output will be given by I0. Similarly, we can say that when S1 and S0 represent a 1, it is 01, then the output is going to be I1. We continue like that until we have the final one, and therefore that is what gives us this equation right here, that we are saying that I0 will be at the output when S1 is bar and A0 is bar, and it's going to be I2 when this is 1, 0, going to be I3 when this is 1, 1, and this is the code that represents the select lines. So from that equation that we have just developed, we can then say that 4-line to 1-line multiplexer may be implemented using logic gates that and that forms the internal logic circuit of a multiplexer. It is rather simple because all we are saying is that when we have our 4 input lines and we have our 2 select line codes, then we can be able to determine the output Y by just observing that this is an add operation combined with an OR operation. For instance, we have said that Y is going to be given by I0 when S1 and S0 are both at 0 state. And that is what we are saying, that we can get S1 at 0 state by passing our S1 through the inverter, and we get our S1 bar, and S0 passes through the inverter, we have S0 bar, and therefore our input line comes in here as I0, and for that reason what will be here at the output is this add operation. And therefore, because these select lines can only have one possible combination at a given time, then we are saying that Y will be given by this sum of product of these AND operations, representing each of the 4 possible input lines. What you'll also observe here is that we have an extra input line called CE. CE stands for chip in number, and this acts as a switch for turning on and off this multiplexer. Therefore, what you notice is that when it is, okay, we normally say that this is active row input, and when it is 0, that is when the output of this inverter becomes 1, and the 1 input combines with the add inputs of these AND gates, and that is only when they are going to give a true input that is dependent on I0. If the chip enable pin is given a 1, which is going to come out of the inverter as 0, then all these AND gates will never give any output, because AND gate requires that all the inputs are high for any output to be a high. Therefore, for that reason, we say that this is how we can implement a 4-line to 1-line multiplexer, by simply adding an extra bit of chip enable that we can be able to turn it on or off on need by need basis. And therefore, we can use the symbol as seen here, whereby we have 2 select line inputs and 4 input lines, 1 output line with an extra input line called chip enable, and this is the symbol that we use for a 4-line to 1-line multiplexer. We say that we have an extra input line CE that is added to the circuit, and holding the CE at logic 1 has the effect of producing logic 0 at one of the inputs of the AND gates, and thereby inhibiting the gate. That means the gate will always give an output of 0, and therefore it appears our device multiplexer is off. Consequently, the output Y will be at logic 0 regardless of the logic levels in input levels, and what we are simply saying is that our CE acts as a on-off button for our multiplexer. So CE is referred to as chip enable input, and it is active row. And active row means that it will send an active signal or will turn our multiplexer on when it has received a low input. A low means 0 or off. Of course, off means maybe a bit ambiguous, but when we use state 0 for the input, then we are saying that when we set a 0, our chip enable will be active, meaning that our multiplexer will be turned on.